Welcome to my talk on trans-threshold ion irradiation damage. This will be mainly focused on a single example of primary and secondary mechanisms in one radiation damage system of emerging interest. First, a very brief introduction to my field of radiation damage. My essential contention is that the nuclear industry is critical, and yes, the pun is intended. I won't try to make any more jokes. Nuclear energy is green energy. This is the Pickering Nuclear Station, just a few kilometers east of Toronto. And if you didn't know it was there, you could easily ride your bike right past it and not notice a thing. These 8 buildings quietly sit and produce most of our electricity. In Ontario, more than half of our electricity is from nuclear. 1 in every 2 light bulbs comes from nuclear energy. And the industry is alive and well with multi-billion-dollar refurbishment and some new build efforts underway. And the essential scientific fact which makes nuclear energy so both important socially and economically, as well as a rich environment for material science, is that the nuclear bond is something like 1 million times stronger than the chemical bond. And it turns out deuterium-tritium fusion is even 10 times higher energy density than uranium fission, although this is less energy per reaction. But deuterium and tritium are so much lighter mass, 100 times lighter than uranium, that the specific energy is higher for fusion. So this is going to be necessary for things like colonizing Mars. However, back on Earth, radiation environments, as I've suggested, are a rich environment for material science. In the CANDU reactor, it's made of 480 pressure tubes, which are 6-meter long tubes. They're perfectly round, perfectly straight when you build the reactor. And when you turn the reactor on, every year these tubes grow by 1 centimeter per year. The reason that these tubes grow by 1 centimeter per year is that radiation damage is a process by which massive energetic particles interact with atoms in a material lattice and impart some kinetic energy to an atom in a lattice and knock an atom out of place, pushing it into an interstitial site and leaving behind a vacancy. Here's a little picture from Professor Kai Nordland's research, in which a single particle is given a high amount of kinetic energy. This results in a very fast, over the span of a couple of picoseconds, a melt, and over the next tens of picoseconds, a quench. In CANDU reactors, we have dose on the order of 1 displacement per atom per year. So what is dose? Dose is the essential catch-all parameter which is used to describe the effects of radiation damage. Typically, the more dose something suffers, the more severe the radiation damage effects. This example here I've given is again related to terrestrial fission energy, showing that stress relaxation depends very sensitively on dose in nickel superalloy components. So along with that axial growth that I mentioned, the 1 centimeter per year growth, we also get irradiation-induced creep. And the reason that happens is because that displacement cascade you saw in the animation before, it's like it melts and then freezes. And when it freezes in the presence of a residual stress field, it freezes in such a way as to reduce that stress. So material effects typically sensitively depend on dose. And so then dose has these units of dPa. What is dPa? Displacements per atom. It's not exactly that 1 atom is displaced per 1 dPa, but roughly the energy required to remove an atom from its lattice site normalizes the energy imparted to an atom by an incident massive energy particle. So that is the ratio of the incident energy of your irradiating particle to the energy required to remove a particle from a lattice is going to be approximately the number of defects you create. And this is what we call dose. So the incident energy is controlled by our environment, but this energy required to remove an atom from its lattice is a material property. So this brings us to our first study on damage to tungsten, which is going to be an important material for nuclear fusion reactors. This work is published in Nuclear Instruments and Methods B. So nuclear fission, very well established, very long history. We know its radiation damage effects quite well. What you may not know is that nuclear fusion is in fact a real thing. There's over 100 fusion devices in the world today. Got a very large poster with a list of all the world's tokamaks shown here. I'll just pull out some examples. In Montreal, in the late 20th century, Canada made an important contribution by building the smallest tokamak ever, which contributed to our understanding of the scaling laws required to predict and extrapolate what will happen when we get bigger tokamaks. However, of all these tokamaks that have been built so far, only a couple of them have been able to use tritium. So deuterium-tritium is the target fusion reaction, but tritium handling is a little bit challenging. Tritium itself is a little bit expensive, so this building reactors capable of doing DT fusion is really at the cutting edge of, it's the state of the art in fusion. So that means that nothing so far has operated with a continuous high duty cycle DT fusion, and consequently none of the fusion devices so far have suffered the kind of radiation damage that they're going to when they're commercialized. So there's a number of problems with radiation damage to tungsten in the fusion context. One of them is irradiation embrittlement. So power loading is going to be very high. There's going to be thermal stress on the first wall components. So if we build these inner walls out of tungsten, and if they see this power loading up to 10 megawatts per meter squared, that is like enough to vaporize almost, well, maybe anything. So they're going to have to deal with these extreme thermal stresses, and radiation-induced embrittlement could be a deal breaker for this component. However, the state-of-the-art experimental testing of the effective dose on radiation embrittlement in tungsten has only been able to get up to 1 dPa. So fusion reactors, I said fission reactors are 1 dPa per year, but fission reactors are going to be much higher. In power reactors, it might be 100 times this. So the limits of what we can do experimentally when we do not have actual operating devices are quite severe. And with tungsten, we've seen even by 1 dPa, we get the ductile to brittle transition temperature increasing from 400 up to, say, 1200. And so this is, already a significant mechanical detriment. Now, is there anything, I said this TDE is a material property, so is there anything that we can do to exploit materials in order to make a more radiation tolerant component for a reactor? Now, we think back to this NRT model that we've got our dose is inversely proportional to threshold displacement energy. And we look to these recent modeling results in tungsten, where they've used a machine learning informed interatomic potential to make this very fine 5-degree increment map through crystallographic space in all these different possible crystal orientation directions. The threshold displacement energy is calculated by molecular dynamics, and it's predicted that in the 3-2-1 direction, the threshold displacement energy might be 6 times higher than it is in the principal directions. So this leads me to my research question in this case study of, could a 321 textured tungsten be damage resistant? Unfortunately, the experimental evidence is limited. The only crystallographically resolved measurements of threshold displacement energy in tungsten are from the 1970s, and they've only looked at the principal orientations because they've been using single crystal techniques on bulk specimens. Now, what I've done is to look at many grains with much finer sort of spatial resolution than was available in the 1970s. So I have made nicely polished specimens. They have grain size on the order of 100 microns, and they have well-prepared surfaces by electropolishing. I've done ion irradiation with an ion beam to a constant fluence of 10 to the 24 per meter squared at different energies, 500, 600, 800 electron volts. And then I've done EBSD to characterize the orientations of the grains that I've looked at. And so in this one specimen with relatively large recrystallized grains, I'm able to look at a broad sampling of crystallographic space with a large number of different grains. So what I've done with this fancy little piece of metal is nano indentation testing. So this is this fine scale, good spatial resolution testing where I'm able to look at specific grains, the same grains, both before and after irradiation. So what do I see in nano indentation? Well, I do see this radiation-induced embrittlement. This figure, there's 4 different colors going on in this figure. So in blue, we've got unirradiated, and in red, we've got irradiated. So before irradiation, the tungsten exhibits a large, initially elastic response. So you can load it up to 5 millinewtons, and there's no indentation impression left. It's just a purely elastic loading. But then after irradiation, you load it up to 5 millinewtons, and you can see every single indentation impression. So, excuse me. When you load it up to a higher load, 14 millinewtons in purple, in the pre-irradiated specimen, we see that at 14 millinewton loading, the yield load is something like 10 millinewtons. The load at which it transitions from elastic to plastic is about 10 millinewtons. And after irradiation, the load at which it transitions from elastic to plastic is something like 2 millinewtons. So one thing I've seen with nano indentation is that we can do, on a grain by grain basis, testing before and after irradiation to characterize near threshold displacement energy effects. Now, we haven't seen a clear dependence on orientation. So I'll show you these various different specimens. The first specimen we tried at a high energy, sufficiently high energy that we, from previous experience in the lab, had reason to expect that we are creating displacement damage, that we are imparting energy above the TDE. But across these various grains that I've looked at, every single one of them seems to go from before irradiation, shown on the left side of this plot. I'm plotting the yield load. And before irradiation, most of them are perfectly elastic, shown by this break in the axis. And after irradiation, every grain, no matter which orientation, has simultaneously become yielding by 1 millinewton. So this was the highest energy. So I thought, okay, what happens if we do a low energy that we really strongly expect to be below the threshold displacement energy? So 500 electron volt protons, there's basically no observed difference between the unirradiated and the irradiated grains. Almost all of them are purely elastic before irradiation, and after irradiation, still almost all of them are purely elastic. So it really seems like this 500 electron volts is, as we had previously expected, below this damage threshold, or at least we're not seeing any effect of this irradiation condition in our nanoindentation experiment. So I try a medium high energy irradiation condition, 800 electron volts, but with a proton instead of a deuteron. And here with 14 millinewton load testing, we've seen that this average yield load is somewhere around 10 millinewtons. And then after irradiation, the average yield load is going down to something like 2 millinewtons. But I've tried and tried and tried to look for a crystal orientation effect, and despite having sampled a bunch of grains in this 321 orientation where it's expected to have high TDE, I don't find any evidence of reduced damage or any difference in the nanoindentation effect in those grains versus, say, principal orientation grains. Then in a medium low energy condition, the 600 electron volts per hydrogen, we see a little bit of this yield load degradation, but not as much as in the 800 electron volt case. So while we haven't seen this observation of orientation dependence, what we have found is that nanoindentation is a possibly, useful new testing methodology for threshold displacement energy. So previous experimental validation of threshold displacement energy is not so high. That's been okay for fission purposes because using an average TDE of 40 electron volts, as is recommended by the ASTM standard, has worked out pretty well for reactor operations. But for designing next generation materials for new fission reactors, for fusion reactors, I think it's going to be important to get a better grip on TDE, in particular this crystallographic sensitivity to TDE, and this finding that nanoindentation is sensitive to effects in this very small kind of energy window really, to us, strongly suggests that nanoindentation could be a very useful, very high throughput means of assessing threshold displacement energy. Now, some people were concerned that 600 or 800 electron volts is not enough energy to impart radiation damage. So the classical theory says that an 800 electron volt proton beam is only going to transfer 17 electron volts to a tungsten atom. But we know that we should have at least 40 electron volts to knock a tungsten atom out of its lattice site. However, if you do a sequential head-on collision, if instead of a ping pong ball hitting a bowling ball, you have a ping pong ball hit a golf ball, hit a bowling ball, then you can get better kinetic energy transfer, and an 800 electron volt proton beam may transfer more than 40 electron volts. So I've performed ab initio molecular dynamics to try to better understand this. And the lesson that we can draw from this study is that you got to watch out for impurities. Now, everybody's heard this already, that impurities might have a substantial effect on your material system of interest, but in this case, what's happening is that carbon or hydrogen present on the surface of the specimen are able to approach very well in our ab initio molecular dynamics simulations the threshold predicted by the head-on collision approximation. However, the energy transferred to the tungsten atom only reaches this threshold given by the head-on collision approximation when the atoms are sufficiently redirected as to create a direct hit between the impurity oxygen and the tungsten. With this normal incidence hydrogen, we see that the oxygen gets just kind of forced down between the hole over the bridge site on the surface. So it's when your collision, when your energy is substantially redirected, that you may get to the threshold displacement energy. And so therefore, in our experiment, even when we have grains with a surface normal orientation in a high TDE direction, it can be that the damage is caused by surface impurity atoms that are redirecting the beam. So I'm not saying that our experimental results have disproven this crystallographic effect of TDE. However, more controlled, testing to control for the impurities may still find this like crystallographic dependence of TDE. So I'll skip over this. It's just a little cartoon anyways. Come to my conclusions. Radiation damage admits a combined experimental and theoretical approach, and that is a very productive thing to do because radiation damage is inherently an atomic phenomenon, but it does require experimental observations to do engineering. In my thesis, here's a plug to check out my thesis, which is coming out in a few months. It's summarized as 3 lessons. This first lesson is that impurity effects may dominate. I say these are old stories, but with new characters, because everybody knows that, say, differential damage rates may dominate your material system, or that excess energy pushing you away from equilibrium may give you unusual microstructures. But if you want some more specific context of this in the nuclear world, you can check out my thesis. And as a final point for everybody in the audience to take away, really recommend that you try building an atomistic cartoon, something just like what we saw in the previous slide, where there's no real data. I've just kind of drawn a picture for you, but a picture with this atomic scale sensitivity to the effects that I want to illustrate. And it's getting very easy to try and do this yourself. And I think it helps to build a literacy that can be very productive and help you to communicate with some theorist colleagues. Even if you're a pure experimentalist, I think it is still worth it to try to build a little atomistic picture of your material system. So with that, thank you to all of you for being here and paying attention. And I couldn't have made this presentation without you listening, so thank you. And of course, my supervisors, my committee, everybody I've worked with, and to the funding agencies that have supported my work. Thank you.